Hi everyone, my name is Karl, and I team up with Weicheng. Our project is about player detection and tracking in sports videos. We want to see how much we can improve player detection and tracking in wide angle sports broadcast videos. And before we start, let's talk about why these projects matters. So, as me and Weichen did some research, we found out that ACL injuries is actually one of the most feared non-contact injuries in many kind of sports, and the average recovery time is approximately 1 year. So this is the kind of injury that actually creates serious consequences, and we wanted to see if we can flag any of these moments from the videos that can hopefully help teams to protect their players and prevent these injuries from happening. And more specifically, in our case, we team up with Northwestern's women lacrosse teams. They are the NCAA national champions in this year. And so they provide us a bunch of approximately 2 hours broadcast footage and videos among many seasons. The goal is to, again, attract any meaningful insight and hopefully help them prevent this injury from happening. So this is how the project starts. The original goal is to use any post estimation or biomechanical features to work on this videos. But then we discovered that detections were really is not that reliable. Some reason is because of the blurry players that has been missed, and also the ID switching is another issues that we have. So, because yeah, overall the quality of the analysis really dropped dramatically, and so we kind of pivot. We pivot to a new research questions, which is what techniques can we improve player detections and tracking the accuracy and the videos that we have. And this is the pipeline of how it works. So, like I said, they provide a bunch of 2 hours videos footage. But a lot of them are not actually the game itself, right? There's some time off times or players resting or anything. So the first thing that we do is we actually find game clips that's when the players are actually on the field playing, and on average we strength these kind of videos from 2 hours to 73 approximately that times videos. And then what we do next is we detect each players, of course, and then assign an IDs to them. Hopefully, we can do this stably so that on the next stage we can extract data like speed, actions, or directions from it. So this is the starting point that we have, where we use YOLO V8 with byte tracks at 5 frames per second. And the result that we got is about 57 tracks per 30 seconds clip, and on average, 4.4 seconds track durations. So the problem here is pretty obvious. It's that on this 30 seconds footage, we actually got 57 tracks, but there's only about 20-ish players on the field, right? So as we explored a little bit more, we found out that this is just because that the same players keeps getting new IDs every few seconds. And so why does tracking fail when player move fast? We found out that there's two problems. The first problem is that the model itself was trained on still photos, and so the image that we feed in, because of the frames per second that we are using, is maybe not large enough. The motion is blur, which is the main reason why the performance is not that great. And the second thing is that the tracker can reconnect. Like I said, if the frame per seconds can recapture things, more informations, players sprinting faster, then move for example 100 pixels between frames. The box can really overlap, so they kind of treat the players as two different players. So they assign new IDs to them. So, so we did our experiments, right? We try to increase our frames per second from 5 to 10 instead of using byte track, which try to use bot sort to add a little bit of camera motion compensations. We lower a bit of our confidence threshold from 40% to 30%. The reason why is we want to capture more blur players. And more fundamentally, we just use a bigger models, which handles a little bit better uh, for the images, for the videos that we have. And as we combine all these changes together, and we actually can see that there's a pretty significant improvement in terms of stabilities on tracking these players. And so, yeah, these are the research that the results that we have. We can see that for the baseline, we actually only have about five IDs that can survive more than 10 seconds. But as we gradually use different kind of methods, the performance actually increase. In this case, when we are using all combined versions, the improvement is actually under 36%. And so here's comparison that we have for the same moment in the games. We choose this image as is because the reason is that this is when the camera uh, itself is also moving, and as well as the player. The player is moving fast, so it's this is the moment where tracking actually is pretty hard. So we can see that on the baseline. There's only two players detect, and there we can. It's clearly that a lot of the players are not detected. But when we switch it to the all combined versions, most of the players can be detected. So this is the comparison of it. One of the most significant difference is when the camera is actually moving. The baseline models can recaptures when the camera pans are moving. But the best versions not only can captures all these players' IDs, but they make sure that these IDs stays the same. Yep. So after we found we have a more stable models, what we do next is we decided to do a very basic action labeling. The reason the way that we do that is by setting different threshold for the pixel per second. So we have all these kind of actions from standing, walking, running, sprinting to cutting, right? And we use this 5 frames rolling to kind of average out the speed. So in that case, to reduce any camera movement. But as we can see, there is still some limitations for the videos that we have. Now, one thing is still the problem is with the ID. The ID still changed. The average tracking time is still 6 seconds. Um, so it's still not reliable if we want to do individuals level analysis, right? And the second thing is that the speed is not real speed. What does this mean? This means that it's not only just the players are moving, right? The camera is also moving. So let's say if the camera move and the player moves as well, the pixel per second is not exactly what the players are doing. And lastly, the problem is for the camera itself, it can only captures a part of the field, so we can't really see the full pictures of what exactly is happening on the field. So yeah, broadcast video is good for benchmark detecting, but not for individuals biomechanical analysis. And so far at this stage, this is what we have learned. We've learned that there's way by combining different kind of method, we're able to increase the stability for tracking players and increase the percentage of detecting players per frames. And what we can do next is we can try to enable re-IDs so that we use players' appearance to reconnect broken tracks. And hopefully we have have a longer times. We can try to fine tune our YOLO models on more specifically lacrosse videos to fix this motion blurriness issue. And in long term, if we really want to accomplish real-time, real player level analysis, really need a camera that can capture the full field coverage or a multi-camera systems. Yeah, and I want to pass it to Wei Chen's where he'll talk about more a bit about what he have worked with the data set that we have.
Hi, I'm Weicheng. This is part two of our project. Karl just showed how we find and follow the players in the video. I work on the next step. Our very first idea was to look at knee injury risk, which are ACL injuries, from game video. To do that, we need to turn each player's body into simple numbers, like the angle of the knee. That's a part I will talk about. Let me show you where my part fits. Our first goal was to predict ACL knee injury risk from video using body pose, but Karl found a problem first. The players often missed or kept changing ID numbers. If the player data is bad, anything I build on top is also bad, so we split the work. Karl made the detections better. My job was to take those players and turn them into body angle features, the numbers our multi-model injury model could learn from. Here's the basic idea. For each player, the computer marks 17 points on the body, like the shoulders, hips, knees, and ankles. I use the YOLO V8 pose model for this. Then I measure a few simple angles. The most important one is knee valgus. That just means the knee fallen inward, which doctors link to ACL injuries. I also measure trunk lean, which is body tipping over, a sign of poor balance. From the demo picture, you can see the skeleton on each player, the knee angle written on screen, and the red box when the frame looks risky. The math is simple geometry. I take 3 points, the hip, the knee, and the ankle, and I measure how far the knee sticks out to the side from the line between the hip and the ankle. More sideways means more knee falling in, which means higher risk. To keep the numbers clean, I do 3 things. I skip a body point if the model is not sure about it. I smooth the angle over 5 frames so small shaking goes away. And I flag a frame when the angle goes above 15 degrees. The next part is quite interesting because I learned from 2 mistakes. My first Valgri's formula looked correct and ran with no errors, but it was measuring the wrong thing, how much the knee bends, not how much it falls inward. Since everyone running has bent knees, it marks 69% of frames as risky, which is clearly too many. After I fixed the angle, it dropped to 14%, which makes much more sense. The second mistake is that every player was labeled standing. The reason is the camera moves to follow the ball, so even a sprinting player looks still on the screen. After I removed the camera's motion, the speeds became reasonable. Both formula ran fine and were both wrong, so checking them was really important. The referees should not be counted as players, so I had to remove them. My first idea was to find them by color because referees wear black and white, but that failed. In this game, both teams also wear black and white, so it removed real players too. My second idea worked better. Referee shirts have regular stripes, so I count how often the brightness flips from dark to light across the body. Players almost never look striped, so this finds the referees cleanly. On the full game, this removes about 59,000 referee frames from the player data. So far, I tested on short clips, but the real videos are 1.5 or 2 hours long. I did not want to process the timeouts and the scoreboard close-ups, so I wrote a small tool that finds the active play parts by itself. Then I ran everything on a free Colab GPU. For this game, the full video is 128 minutes. My tool found 58 windows of real play. That is about 83 minutes kept, and it produced about 219,000 player snapshots. All the measured angles are saved as simple JSON and CSV file for the next model. These are the results from the whole game, about 392,000 knee angle measurements. The left chart shows that most knee angles are small and safe. The middle value is only 3.5 degrees, and only about 1 in 10 frames is flagged. The middle chart shows what players were doing, mostly standing and walking, with some running and sprinting. The right chart is interesting. A few segments have many flagged frames. Those are the moments a coach might want to review. I think this is the most important useful output because it points to specific moments instead of just one big number. I also wanted to check how correct the body points really are. So I looked at 26 players by hand and scored each joint. The result is clear. For big players close to the camera, the points are almost always right, about 100% for the ankle. But for small, far away players, the ankle is wrong almost every time, about 0%. And the ankle is the joint we care about most for the knee. One more thing I noticed is that the model often says it's sure even when the point is wrong. This confirms what our professor mentioned in class doubts a confidence score. I want to be honest about the weak points. The biggest one is that I cannot follow a single player throughout the game yet. Across these games, the tracker made about 9,200 different ID numbers for only about 24 players, because IDs break after each sprint or block. So for now, I report game totals, not one player stories. Also, small players are blurry, so their knee and ankles are often wrong. The angle is only a 2D guess from one camera, so it is a rough screen, not a medical measurement. And the speed still has no real-world meter scale. So if I had one more month, here's what I would try, roughly in this order. First, I'll follow each player using their appearance so the IDs stop breaking. Then I could make real one-player stories. Second, I used the field lines to turn pixels into meters to get true speed. Third, uh, I left the body points into 3D to measure the knee angle more correctly. And fourth, train the model on blurry sport video so it stops missing the small, fast players. So to finish up, here's what I learned. My first answers went wrong, but checking them was the real work. I am new to computer vision, so I kept things simple and checked carefully. The biggest lesson for me is that a formula can run perfectly and still measure the wrong thing. So we always have to test it against the real data. In the end, we build the full path from video to body points to knee angles and to risk numbers that can feed our ACL model. Thank you for watching.